Welcome to this explainer. If you're deep into studying electrical engineering right now, or honestly, even if you're just a bit curious about how the world actually gets powered, chances are you've bumped into some pretty intimidating textbooks today. You've probably been staring at pages packed with complex differential equations and, well, Greek symbols that can just make your head spin. But tonight, we're going to set all that heavy math aside. We're treating this like a late-night, unhurried study session. We're just going to look at the simple, beautiful concepts behind the math. We're demystifying reactive circuits, and we're going to do it not by crunching numbers, but by understanding the calm, natural way energy actually moves.
So it's a gentle, almost philosophical question, isn't it? Have you ever actually wondered what happens to energy that a circuit receives but doesn't really need to consume right away? When we're looking at standard engineering problems, it's so easy to get trapped in this mindset that energy only has two states, like it's either sitting in a battery or it's being aggressively burned up to do work, glowing in a light bulb or spinning some heavy motor. But nature is rarely that black and white. Sometimes energy just needs a place to hang out for a fraction of a second. It doesn't need to be destroyed, and it doesn't need to be permanently used. Reframing our perspective to see a circuit as this living, breathing system that can gently hold on to energy, that really changes everything.
Section 1. Understanding energy consumers. So, to really grasp how a circuit holds on to energy, we first need to set a quick, gentle baseline of how energy usually behaves in those simple, everyday circuits we're all familiar with.
Right, looking at the foundational notes on basic electrical engineering, electrical power is defined beautifully and simply. It's literally just the rate at which work is done. If you glance at the math, it's just voltage times current. P equals V times I. This is our steady, familiar, real power. When current flows through a wire and pushes against a resistance, actual work is happening. Heat is being generated. Think of your laptop fan screaming while you're rendering an assignment, or a mechanical shaft is turning. This is the heavy lifting of the electrical world. It's power being actively, permanently transformed from electrical energy into something else entirely. Okay, let's dive into this, because this distinction is the absolute bedrock of everything we're covering. In any electrical network, we've got active elements and passive elements. Active elements, like your voltage or current sources, well, they're the pumps. They're the heartbeats supplying energy into the system. But on the flip side, we have passive elements. The most famous one is the standard resistor, which permanently dissipates energy away as heat. But notice the second part of that definition, or store energy. Not all passive elements are these hungry consumers. Some are more like quiet librarians. They just check the energy out for a little bit, keep it safe, and fully plan to return it. Moving on to Section 2, meet the energy stores. Let's shift our focus away from those permanent consumers and meet the components that make a circuit behave differently, the ones that introduce just a little bit of memory and patience into our networks. I love pulling this exact phrase straight from Chapter 3 of the textbook. Analysis of simple circuits with storage elements. Textbooks can sound so incredibly dense sometimes, right? Like, when you hear the phrase reactive circuits in a massive lecture hall, it sounds like something volatile or highly complex. But look at how it's actually defined there in parentheses. It just means a circuit with storage elements. That's literally it. Reactive just means we're introducing elements that store energy rather than permanently burning it up. So, in the electrical world, we essentially have two fundamental borrowers. Two beautiful components that just hold on to energy without wasting a drop of it. First, we have inductors. They store energy safely and quietly in a magnetic field. They resist sudden changes in current, acting sort of like a heavy flywheel that just wants to keep spinning smoothly. And second, we have capacitors. They store energy peacefully in an electric field. They resist sudden changes in voltage, kind of like a water tank that slowly fills up and gently smooths out the pressure. Neither of these burn up energy like a resistor does. They just hold it. Now, what's really interesting here is looking at how a simple pulse of current affects a capacitor. As we can see with the curve for W, which stands for work or energy, it isn't some harsh, jagged spike. It's this gentle, sweeping curve rising upward over time, a nice square law rise. The electric charge builds up, the voltage gradually increases, and the energy accumulates beautifully and smoothly within that electric field. Nothing is being destroyed here at all. The circuit is literally just taking a deep breath in, storing that energy perfectly.
All right, Section 3, the reactive energy slosh. We know resistors consume energy, and we know inductors and capacitors just store it. But what actually happens when we bring these components together in an alternating current system? Let's get into the climax of our study session here, completely free of any terrifying calculus.
Think about when you plug something into the wall. You're dealing with alternating current, AC power.
The voltage and current are constantly shifting, pushing, and pulling in a sine wave. In this environment, reactive power really isn't a complex math problem that you need to stress over. It is simply energy sloshing back and forth between the power source and those energy stores we just talked about. Imagine the tide gently rolling up onto a beach, filling a small tide pool, and then peacefully rolling back out into the ocean. That borrow and return process? That is exactly what reactive power is. The capacitor or the inductor fills up with energy as the AC wave rises, and then it empties that exact same energy right back into the circuit as the wave falls.
Let's break down how this builds such a complete, elegant system. In an AC circuit, you have this beautiful division of labor. First, the real power, that P equals VI we mentioned earlier, is steadily being consumed by the resistors to do actual work, like keeping your desk lamp on. Second, the reactive energy is temporarily being borrowed by the inductors and capacitors to maintain their magnetic and electric fields. And third, and honestly most importantly, no actual power is lost in that reactive exchange. The energy sloshing back and forth is a zero-sum game. The power company's generator pushes the energy out to the capacitor, and a fraction of a second later, the capacitor pushes it right back.
And there's a fantastic quote from a footnote in the steady state analysis chapter that captures this perfectly. The average of a sinusoidal current over one cycle is 0. I really want you to let that sink in for a second because it's incredibly reassuring. You might have pages of wave equations and phase angles to deal with eventually, but fundamentally, nature just loves equilibrium. All of that intimidating movement, all the peaks and valleys of an alternating wave, they eventually balance out to a peaceful, perfect 0 over a full cycle when we're talking about pure reactive sloshing. It all comes back home.
Which brings us to Section 4, a peaceful closing thought. As we wrap up this explainer, I want to leave you with one final concept from the engineering side and then tie it right back into how you approach your own work.
So the crucial point here is that engineers don't just let energy slosh around chaotically. There's a concept from our sources called impedance matching. In a circuit, the goal is often to transfer maximum power from a source to a load. To do this efficiently, engineers have to delicately balance the circuit's active consumers, the resistance, with its passive storers, the reactants. When they find that exact mathematical sweet spot, the energy flows perfectly. There's no chaotic bouncing, no wasted effort. Nature, and electrical circuits by extension, ultimately just want to find a steady state of optimal harmonious balance.
And that actually brings us right back to you. Think about your own energy tonight. You have active energy, right? The hard work, the studying, the problem solving, the times you are actively burning calories to get things done. But you also absolutely need reactive energy. You need moments to just pause, absorb the information, gently store it without forcing it, and let your mind slosh back to a state of rest. Just like a circuit perfectly balancing its active and reactive elements for maximum efficiency, how can you find a steady, unhurried balance in your own habits? You don't have to output maximum power all the time. Sometimes it's more than enough to just peacefully store the energy for tomorrow. Rest well, let the concepts settle, and I'll see you in the next explainer.